Yes, it started.
Okay, welcome. We're going to continue with where we left off. Now, the previous slide, that was not the previous slide. We talked about specific heat. Your book goes into much more detail, so I hope you read or will read. So, I left off with a discussion about how water is very resistant to changing temperature due to its high specific heat. It takes a lot more heat to to raise the temperature of water than it does other liquids like water. All right, now, for the same reason, water kind of hangs on to that heat and it takes longer to cool it off as well. More heat has to kind of be lost before water will start cooling off. So that's a good transition into the difference between what happens when you freeze water and what happens when water is in its liquid state. Now, hopefully, some, most, or all of you have been able to read this section or these sections already, so you might have looked at this diagram and know kind of what I'm going to say. But I want to point out some things. One is something you don't have to write down, which is this. There are many different types of ice. But since you probably have never left this planet, and since you probably don't have the hundreds of thousands of dollars of equipment to create crazy amounts of pressure in a chamber, you've probably never seen any other kind of ice. And I haven't either. The type of ice we have on Earth and that we talk about with living things is actually called ice 1H. Don't write that down, but just think about that. Isn't that weird? Isn't that weird?
Yes.
Yes, it is weird, or at least I think so. You could have said no, it's not a big deal. The H stands for hexagonal, because when water molecules enter into a solid state, they create this beautiful honeycomb structure that has a hexagonal shape to it. So water molecules will arrange themselves in shapes like hexagons, and it's still hydrogen bonds that are causing them to be attracted to one another. And because of those hydrogen bonds and all the forces that are being exhibited, they take on this very interesting geometry. Ice 1H. Ask for it at a restaurant, specifically. Now, here's what happens. When these crystals of ice form, these hexagonal shapes take up a lot of space. Solid ice, as you may have seen when you put a bottle or a canned beverage into a freezer, will do what? It expands, and it can actually burst the container that you have it in. That is a possibility. Because of that expansion, ice is less dense than liquid water. And here's why. This is a diagram of ice with these nice hexagonally shaped crystals. Once you start heating ice up, that heat is going to make all the molecules do what? Move and vibrate faster. There are actually, even if it's a solid chunk of ice, all those water molecules, while being locked in place, they're vibrating at insanely high frequencies. But when you add enough heat, those vibrations become so intense that the house of cards falls. And these crystals collapse into a chaotic mess that's still kind of sticky that we call liquid water. Now, when those particles collapse, they become more dense because they're closer together. So solid water or ice is less dense than liquid water. So where do you find the ice in a frozen body of water?
At the top.
At the top. It's less dense, so it's at the top. And since it's such a good insulator, since it's so resistant to temperature change, what ends up happening in nature on Earth is that you have a real resistance to an entire body of water freezing. Because ice will form at the top and then kind of insulate the rest of the liquid water. And there are many organisms that rely on that concept. They have a little shrimp here with the surface of the eye of water frozen over, but it's still living beneath it. If ice was heavier or more dense, it would sink to the bottom and you wouldn't have that protective insulating layer. So keep that in mind. Okay, last idea here. Keep going the wrong way. The last idea here is water as a solvent. Water is a very good solvent because it is polar and because it has a positive and negative end. And here you see a process that you will actually be able to witness in the lab. I've got some salt over here that we're going to use in the lab, and we're going to make a salt solution with a certain molarity. Remember that from chemistry? Molarity? Good, yes, some people remember. Good. But what happens when you dissolve substances into water is actually, I guess, a little different, whether it's an ionic substance or a covalently bonded substance. But in this case, we see salt in a beaker of water. And here we have the chloride anions and the sodium cations. Good. Very good. All right, now the cations are positive, the anions are negative, but water is what? Slightly both. It's slightly both. There is a negative end on what part of the water molecule? The oxygen end. And there are slight positive charges on the hydrogen end. All right? So what ends up happening when water molecules come in contact with salt, and this is kind of what salt would look like if you could see the individual particles. It's just these ions that are stacked, in a block or a cube in the case of salt, that are kind of alternating in their charge. Well, when a water molecule gets close to or collides with a piece of salt, the slight positive charge on the hydrogen end will just kind of pick at the negative chloride anions. And eventually, it can wrench them free. And the process just keeps happening. What can you do to speed up this process?
Stir it.
Yeah, you can stir it. Or
Heat it up.
heat it up. What does stirring and heating it up actually do?
Moving the molecules.
That's right. You are creating more collisions between the water and the substance the water is dissolving. Water, in this case, is the solvent. What do we call the particles of salt? The solute. Together they will make a solution. Very good. All right. That's stuff that you should know from chemistry. Your book talks about these hydration what do they call it? Shells. Sorry, I blanked. Hydration shells where water will surround the ions. Okay, but that's not just with salt. You can do it with sugar and huge molecules. This, you can see all the water molecules but in the kind of purple are all the atoms of a very large protein. We'll talk about proteins by the end of this unit, but some proteins can be dissolved by water. Into what kind of solution? What's a water-based solution called? Aqueous solution. That's right. That's the kind of solutions we're talking about here with water specifically. And here what you can see is water molecules creating that same hydration shell surrounding this entire protein molecule. And if you have a bunch of these protein molecules, you have a chunk of like lysosine or some kind of protein, or that's an amino acid, but an amino acid or protein that will dissolve in water. Even if it's very large, the water can still surround it and kind of carry it off into the solution. Now, what does this large molecule have to have for water to be able to do that? It has to have some positive and negative charges. And that's what this whole side thing is here. If there are partial charges on the substance, water should, given enough time, be able to dissolve it. Now, here's where it gets a little bit weird. Something like lipids, which are your fats and oils. And we have a flask of oil over there you're going to use today. Vegetable oil doesn't have these positive and negative slight charges all over it. So what does water do? Yeah, it just doesn't stick to it, and they don't really mix. They are chemically very different, and it's all based on these slight charges. That's actually where I wanted to get last time, but we kind of ran out of time. So before you stop the video, you're still recording, right? Good. Before you stop the video, we're going to do a lab now. As I mentioned, I'm going to try to put you into groups of 3, but we're going to have one group of 2, so that group will not have to do a video. But we're going to record, we're going to have one person in your group record the other 2 people working. Now, you don't have to record every single painful drip and drop that we will be seeing in this lab, but we can kind of cut the video at times and pick it back up. But I do want all of you to have a video recording of what your lab group does. The easiest way is just my column here, and we're going to go 3 as a group, 3 as a group, 3 as a group, and then you 2 will work together. But since there's only 2 of you, you don't have to do a video. So the videos will, or the best video will be put on the coursework page, and you can watch it at home if you're not here and use the data from that lab. You can stop the video.